So far all the kinematic relations that we derived, were based on pure math. No observation was necessary to derive them. Next we are going to perform some physical experiments. Take measurements. And make observations. In order to derive the equations of motion, for an object moving along a one-dimensional frictionless path. The experiments that we are going to present, were performed many centuries ago by scientists such as Galileo and Newton. In order to systematically study how objects move in our physical reality, we must try to find all the physical influences that affect the motion of an object. Then we will try to eliminate all these influences, except for one influence, so that we can come up with a general description of how this one influence affects the motion of the object. Here is a list of influences that we can observe in our everyday common life, which affect the motion of objects. The initial motion state of the object. Direct contact with other objects. Direct contact between two objects results in normal reaction forces, and/or tangential friction forces between the objects. Air resistance, gravity, electricity, and magnetism. In this section we will come up with experiments that attempt to eliminate all influences, except for the initial motion state of the object. We will do this in order to study how the initial motion state of that object affects the subsequent motion of the object. But first, let's briefly describe each influence, so that we'll know how to eliminate it. We can observe that the initial motion state of an object affects its subsequent motion in a predictable way. Let's observe, for example, a basketball being tossed into the air. If we know the initial motion state of the ball at one point in time, then we can predict the subsequent motion of the ball. Note that we don't need to know what caused that motion to begin with. Another example is a billiard ball moving on a billiard table. The ball has an initial motion state that causes the ball to continue moving across the table. If we know this initial motion state, then we can predict the subsequent motion of the ball. Direct contact between objects is the most common influence that we can observe that affects the motion of objects. Direct contact influences are manifested in two ways. Normal reaction forces that act normal to the two surfaces in contact, and friction forces that act tangentially to the two surfaces in contact. Next I'm going to try to explain each type, using some common examples. A normal reaction force is an influence that is imparted by one object onto another object, when the two surfaces of the objects are in direct contact, like the two rocks shown here. This influence acts in the direction of the common normal to the two surfaces at the contact point. The normal reaction force influence is the reason why solid objects don't intersect, but rather push against each other. It is the reason, for example, why you can sit in a chair without going through the chair. Another example of normal reaction force influence is shooting a basketball. The player's hand imparts a normal force on the ball, in a direction that is normal to the common tangent between the hand's surface and the ball's surface. This normal force changes the motion state of the ball. Once the ball leaves the player's hand, then the initial motion state imparted by the player's hand causes the ball to continue moving. Another example is a cue hitting a ball. The cue imparts a normal force on the ball that is normal to the common tangent between the cue's surface and the ball's surface. This normal force changes the motion state of the ball. Once the cue is no longer touching the ball still continues to move, because it has an initial motion state that affects its subsequent motion. Rocket propulsion is another example, in which case the exhaust of the rocket is exerting a normal force on the bottom of the rocket, which pushes the rocket up. We will study normal reaction forces in the dynamics and statics chapters of this course. Friction is an influence that acts at the contact point between two surfaces. Friction acts along a line that is tangent to the two surfaces that are sliding past each other. It acts in the opposite direction to the tangential relative velocity between the two surfaces, and always tends to reduce that relative tangential velocity. Friction is the reason why you can stand on an inclined surface without sliding down. Another example of friction influence is a block sliding on a table. If the block has an initial velocity v0, parallel to the surface of the table, friction will tend to reduce the velocity of the block in time, till it becomes zero. We will study friction in the dynamics and statics chapters of this course. Air resistance for an object moving through air is caused by air molecules hitting the surface of the object. Air molecules hitting the surface with a relative velocity component, normal to the surface, like the red molecules shown here, generate normal reaction forces. Air molecules hitting the surface with a relative velocity component, tangent to the surface, like the yellow molecules shown here, generate friction forces. The combination of both forces causes the relative velocity between the object and air to decrease. An example of air resistance is an object suspended by a parachute falling through air. Without the parachute, the object falls much faster. The parachute generates a lot of air resistance that reduces the object's velocity as it falls. Airplanes, cars, birds, and humans all encounter air resistance as they move through air. Air resistance tends to reduce the relative velocity between the object and the air. Air resistance is due to both normal reaction and friction forces between an object and air. We will study air resistance in the fluid dynamics section of this course. Gravity is another major influence that affects the motion of everyday life objects. Gravity causes objects to fall down when they are not supported. For example, if we release a stone from a tower, the stone will start moving down due to gravity. Gravity is an influence that tends to increase the velocity of objects downwards, towards the center of the Earth. Gravity affects the motions of all objects that are free, in other words not supported, in the vertical direction, such as balls, birds, and airplanes. We will study the motion of objects due to gravity later in this chapter. Electric charges affect the motion of objects. For example, let's rub a rubber bar with fur. This creates an electric charge on the bar. Then let us bring the bar close to a styrofoam peanut, hanging by a thread, that also has an electric charge of the same type. We observe that the peanut moves away from the bar. The bar affects the motion of the styrofoam peanut through static electricity. Electric motors are another example, where electricity is used as an influence to rotate the spindle of a motor. We will study electricity and electric forces in the electricity and magnetism part of this course. Magnetism affects the motion of objects. Suppose we have a steel magnet on a table. If we bring a second magnet close to the first magnet, we observe that the first magnet moves, even though the magnets are not touching. This motion is a result of magnetic forces between the two magnets. We will study magnetism and magnetic forces in the electricity and magnetism part of this course. Now that we identified the various common influences that affect the motion of objects, let's try to study the effect of just one influence on the motion of an object along a one-dimensional path. The influence that we first choose is the initial motion state of the object. This is the first obvious influence to study, since this influence actually cannot be eliminated. Any object has an initial motion state defined by its position, velocity, acceleration, and higher-order motion time derivatives. At a certain initial point in time, say t0. Let's try to devise an experimental setup of a particle moving along a one-dimensional path, with no other influence except for an initial motion state. We therefore have to eliminate the rest of the influences that can affect the motion of the particle, namely normal reaction forces, friction, air resistance, gravity, electricity, and magnetism. Here is an experimental setup that approximates a particle moving on a one-dimensional path. The one-dimensional path is a smooth, linear aluminum rail, with a C cross-section. We place a smooth cylindrical puck on the rail. The diameter of the puck is just a tiny bit smaller than the width of the rail. In the last slide, we talked about how we are going to eliminate all influences except for the initial motion state. Now let's go over each of these influences, and I'll tell you how we plan to minimize each one for this experiment. There are no solid obstructions along the 1D path. Thus there are no normal reaction forces. Next, we are going to eliminate friction. The rail and puck are very well lubricated. Thus, the puck actually moves on a thin layer of oil along the rail. And the solid puck's surface and rail's surface are not in direct contact. This minimizes friction between the puck and the rail. Alternatively, the rail could have a series of small holes along the bottom of the path through which air is pumped. In that case, a thin air layer separates the puck and the path, which reduces friction. So, let's assume that using either oil or air lubrication, friction effects between the puck and the path are negligible. Air resistance is minimized because of the following three conditions. First, the puck has a much higher density than air. Second, the puck has a relatively small attack surface area through which it is moving through air. And lastly, the maximum velocity of the puck relative to air is small. We place the path horizontally, such that there are no gravity effects. Recall that gravity only acts vertically towards the center of the Earth. Static electricity effects are very small. But, they can be virtually eliminated by touching the puck with a wire that is connected to ground. And, by making sure that the path is grounded. The puck and rail are made of plastic or a non-magnetic metal such as aluminum, such that there are no magnetic effects. Thus we've eliminated all influences except for the initial motion state. We are going to give the puck an initial motion state by simply pushing it with our hand, then letting it go. Then, we will measure the position of the puck on the path, from an origin point O, on the path. We can do this in many ways. We can place marks at equal distances on the path. Then, use a camera to capture the position of the puck along the path. We record the puck position for time t1, t1 plus delta t, t1 plus 2 delta t, etc. Where delta t is the time between camera frames. We can also use a linear optical encoder, and get time versus distance readings directly using a computer connected to the encoder. We can also use a laser distance sensor, which measures the distance between a laser sensor and a target attached to the puck. After giving the puck an initial motion state by pushing it with our hand, we will record the position versus time of the puck for 2 seconds. If the camera or distance measuring device that we are using can capture 25 frames per second, then, we get 25 readings for the position every second, or 1 reading every 0.04 seconds. Now, let us give the puck an initial push, then, we let it freely move along the track. The graph shows the values of the position of the puck. From time 0 to time 2 seconds along the one-dimensional path, every 0.04 seconds. At time 0, the position of the puck is 0.34 meters. At time 0.04, the position of the puck is 0.3668 meters. At time 0.08, the position of the puck is 0.3936 meters. At time 0.4, the position of the puck is 0.608 meters. At time 1.0, the position of the puck is 1.01 meters. At time 2.0, the position of the puck is 1.68 meters. If we connect these 50 points, we get a graph of position versus time that looks like a straight line. Therefore, we can postulate that x of t is given by the equation c1 times t, plus c0. Let's use 2 points from the experiment to find the coefficients c0 and c1. We can choose any 2 points, and so let's choose the first and last points of the experiment. At the first point, x at t equals 0 is equal to 0.34. So we have c1 times 0 plus c0 is equal to 0.34. And therefore, c0 equals 0.34. Or in other words, c0 is equal to x of t0, or simply x0. At the last point, x at t equals 2, is equal to 1.68. Which implies that c1 times 2 plus 0.34 equals 1.68. And therefore, c1 is equal to 1.68 minus 0.34, over 2. And so c1 is equal to 0.67. Which is the slope of the x versus t curve. Therefore, x of t is equal to 0.67 times t plus 0.34. Let's verify that we can use this equation to find the value of any point on the x versus time curve. For example, at t equals 0.4 seconds, x was found in the experiment to be equal to 0.608 meters. So let's substitute 0.4 for t in our equation. And we do indeed get 0.608. Let's check another point. At t equals 1.0 seconds, x was found to be equal to 1.01 meters. If we substitute 1.0 for t, we get 1.01 meters. And again our equation matches the results found by the experiment. Recall that the equation of position versus time, for constant velocity motion, is x of t is equal to v0 times t plus x0. You may click on the shown link to review that section. Therefore the initial position, x0, is the value of c0. And the constant velocity, v0, is the value of c1.